Hello everyone, I am Vedang Sawarkar 19 BC 1303 and today we will learn about Bitcoin scripts. This is digital assignment 1 under the course Blockchain and Cryptocurrency offered in Vellore Institute of Technology Chennai by Dr. Ganeshan R. Bitcoin scripts. So what is Bitcoin scripts? What is the need of Bitcoin? Let us see. Bitcoin script is the language Bitcoin uses to do everything it can do, from sending funds from a wallet to allowing the creation of multi-user accounts. To understand scripts, the easiest way is to understand by an example. We will take as an example that the most common script in Bitcoin, which is to redeem a previous transaction output by signing with the correct public key. So traditionally, these two scripts called script sig and script public key. That is because in the simplest case, the output script is just specifies a public key or an address to which the public key hashes, and the input script specifies a signature with that public key. When a transaction is being validated, these two scripts get pasted together or concatenated. There, they are executed, and if the script runs without any error, it is considered as valid transaction. There are only two possible outcomes when a Bitcoin script is executed. It either executes successfully with no errors, in which case the transaction is valid, or if there's any error while the script is getting executed, the whole transaction will be invalid and shouldn't be accepted into the blockchain. So where did the scripting language come from? It doesn't really have any proper name. It's just called script, or you can call it Bitcoin scripting language. And it was built specifically for Bitcoin. It is most inspired that the language called Forth, which is a old stack-based programming language. But you do not need to understand Forth to understand Bitcoin scripting. The key design properties here were to have something that was quite simple, compact, but yet had support for sophisticated cryptography. So this scripting language consists special purpose instructions to compute hash functions, to compute and verify signatures. So there are a lot of limits here which are to be kept in mind. In particular, there are no loops in Bitcoin scripting language. Every instruction is executed exactly once in a linear manner. So, just by looking at the script, we can determine how long it will take to run the script and how much memory it can use. This is not a Turing complete language. It does not have the ability to compute arbitrarily powerful functions, and this is by design because the miners have to run these scripts, which are submitted by arbitrary or random participants in the Bitcoin network. So, you don't want to give them the power to submit the script that might have infinite loop or the script might run forever. So basically, it cannot be exploited by miners for their own benefit. Since this is not a Turing complete language, we don't have the halting problem. So any Bitcoin script will surely terminate within a finite number of steps, which is just the number of instructions in the script. The most common script in Bitcoin is Bitcoin transaction validation script. The script where the sender of the coins simply specifies the public key of the recipient, and the recipient of the coin to redeem them has to specify a signature using that specified public key. So now let's look at some of the common Bitcoin scripting instructions. First instruction is OPDUP. It is used to duplicate the top item of the stack. Whatever the input is, this instruction will duplicate the item that is present at the top of the stack. Secondly, OP hash 160. This instruction hashes the input twice, first with SHA-256 hashing algorithm, then with RIP-EMD 160, which increases the output length to 160 bits, and increases the security level of the hash function. Third is OP equal. Verify. OP equal verify is used to check the top two values of the stack. It returns 1 or true if the inputs are exactly equal, 0 or false otherwise. It then marks transaction as invalid if the returned value is not true, and otherwise the value is removed. OP checks SIG. It checks that the input signature is a valid signature using the input public key for the hash of the current transaction. Check multi-sig compares the first signature against each public key until it finds a match and continues the process for other public keys. It is repeated until all the signatures have been checked. All the signatures need to match a public key. If all signatures are valid, 1 is returned, 0 otherwise. It is built-in support for joint signatures, so this checks multiple signatures with one instruction. Now, let us see how does the script exactly gets executed and validates the transaction. So, the first two instructions in the script are just the data instructions. These are the signature and the public key used to generate that signature. And these were specified by the recipient in the script sig component or the input sig. So, the first two instructions in the script are just the data instructions. These are the signature and the public key used to generate that signature. And these were specified by the recipient in that script signature component or the input script. So, executing data instruction is easy in a stack-based language. If you see data, just push it onto the stack, and that's the only interaction with the memory that you have in the stack-based programming language. There are no variables. There is only a stack. So the only thing you can do to write data to memory is to push it onto the stack. So when the first data instruction sig is observed, it is pushed onto the stack, followed by the next data instruction pub key, which is public key of that signature. Now we will start executing the second half of the script, which is specified by the sender of the coins. So this is the script public key component of the script. Now we are going to start to actually manipulate some of those values on the stack. So this duplicate instruction OPDUP says to simply take the value that's on the top of the stack, pop it off, and write two copies back onto the stack. So we are just going to duplicate that public key. So this is duplicate instruction OPDUP. It says to simply take the value that's on top of the stack, pop it off, and write two copies back to the stack. So we are just going to duplicate that public key. The next instruction, hash 160, says that take the top value of the stack and compute a cryptographic hash of it. So this top value is going to be converted from public key into a hash of the public key. Now, the next instruction is a data instruction which will just push the data onto the stack. This is a public key hash specified by the sender which had to be used to generate a signature to redeem these coins, and the previous instruction which converted the public key to hash was the public key specified by the recipient. So now at the top of the stack we have two values, the hash of the public key as specified by the sender and the hash of the public key that was used by the recipient when trying to claim the coin. So next is the equal verify command, which will just check whether the two values at the top of the stack are equal or not, and if they are not equal, an error is thrown and the script will stop executing. So assuming that both the public key hash matches, then this instruction will consume those two data items that are at the top of the stack. Now we are left with two data items on the stack, the signature and the public key. We have already checked that the public key specified was the right public key, and now we check the signature is valid or not. Check sig instruction verifies the signature with the public key. So this is where the power of Bitcoin scripting language comes into play. There is just instruction that lets you verify a signature. So it is easy to write scripts that do signature verification without calling any special library to check the signatures. That's all built into the Bitcoin scripting language. This signature is the signature of the entire transaction. So this instruction will verify that the entire transaction was successfully signed. This will pop those remaining items from the stack, check that the signature is valid. So now we have executed every instruction in the script and the stack is empty. If there are not any errors, the output of the script will be a simple yes. So every Bitcoin script can only produce two possible outcomes when a Bitcoin script is executed. It either executes successfully with no errors, in which case the transaction is valid, or if there's any error while the script is getting executed, the whole transaction will be considered invalid and shouldn't be accepted into the blockchain. So, a little bit more about the Bitcoin scripting language. It is very small. There is room for only 256 instructions because each one is given one byte. Out of these 256 instructions, 15 of them are currently disabled, so you can't use them at all. And 75 of them are reserved, so haven't been assigned any specific meaning yet, but they might get added later in the future soon. So there are basic arithmetic instructions, basic logic like if and then throwing errors, etc. And finally, there are crypto instructions like hash functions, instructions for signature verifications. As of today, this script is not used very heavily. So, if we look at the history of Bitcoin and see what scripts haven't been used, the vast majority, 99.99%, are exactly the same script that we saw in our script execution example. A script that just specifies one public key and requires a signature for public key in order to spend that coin. There are few other things that have some use. So there's multisig that gets used a little bit, and there are a special type of scripts called pay to script hash, which also gets used a little bit. There hasn't been too much creativity in terms of what Bitcoin scripts people use, and one reason for that is that the Bitcoin nodes by default have a wide list of scripts and they refuse to accept the scripts that they consider not standard. So some of the scripts are called proof of burn. It is a script that can never be redeemed. So, if you have a proof of burn script, it is provable that those coins have been destroyed and there are no possible way for them to be spent. This is quite easy to implement. You just have to use this code OP and this is quite easy to implement. You just have to use the code OP return which throws an error if it has reached. Because of the error is thrown, the data in the script that comes after OP return will not be processed. So this is an opportunity for people to put arbitrary data in a script and hence into the blockchain. If for some reason you want to write your name or if you want to timestamp and prove that you knew some data at a specific time, you can create a very low level very low value Bitcoin transaction. You can destroy a very small amount of currency, but you get to write whatever you want into the blockchain, which should be kept around forever. Now, let us look at some of the applications of Bitcoin scripts. The first application is escrow transactions. Suppose that Alice and Bob want to do business with each other. Alice wants to pay Bob in Bitcoins for Bob to send some physical goods to Alice. In normal case, Alice and Bob are honest, and once the good arrive on time with Alice, Alice releases the money from the escrow to Bob. But in case of a dispute, Alice doesn't want to pay until after she has received the goods. But Bob doesn't want to send the goods until after he has been paid. What can we do about that? A nice solution would be to get a judge involved, which in this case is Judy. Judy will decide which of these two are honest. If Judy decides that Bob has cheated, she will send the money back from escrow to Alice. If Judy feels that Alice is simply refusing to pay when she should, she will send Alice's money from escrow to Bob. So Judy has full control here, but she does not have to get involved unless there is a dispute. Another good application is Green's address. Suppose Alice wants to pay Bob and Bob is offline. Since since he is offline, Bob cannot look at blockchain to see whether a transaction that Alice is pending is there or not. It is also possible that Bob is online but doesn't have the same look at the blockchain and wait for the transaction to be confirmed. We want the transaction to be in the blockchain and be confirmed by 6 blocks, which takes up to an hour before we trust that it is really in the blockchain. But for some merchandise, such as food, Bob can't wait an hour before delivering. To solve this problem, to solve this problem of being able to send money using Bitcoin without the recipient accessing the blockchain, we have to introduce another third party, which we'll call the bank. In practice, it could be any exchange or any other financial intermediary. Alice talks to her bank. Hey, it's me, Alice. I am your loyal customer. Here's my card or identification. And I would really like to pay Bob here. Could you help me out? And the bank answers, let's say, sure, I'm going to deduct some money from your account and draw up the transaction transferring the money from one of the green addresses to Bob. Third example is efficient micropayments. Suppose that Alice is a customer who wants to continually pay Bob small amounts of money for some service that Bob provides. For example, Bob may be Alice's wireless service provider and requires her to pay a small fee for every minute that she talks on a phone. We want to combine all these small payments into one big payment at the end. It turns out that there is a neat way to do this. We start with a multi-sig transaction that pays the maximum amount Alice would ever need to spend to an output requiring both Alice and Bob to sign to release the coins. Now, after the first minute that Alice has used to service, she signs a transaction spending the coins sent to multi-sig address, sending 1 unit of payment to Bob and returning the rest to Alice. After the next minute of using the service, Alice signs another transaction, this time paying 2 units to Bob and sending the rest to herself. Notice these are signed only by Alice and haven't been signed by Bob yet, nor are they being published to the blockchain. Alice will keep sending these transactions to Bob every minute that she uses the service. Eventually, Alice will finish using the service and tell Bob, I'm done, please cut off my service. At this point, Alice will stop signing additional transactions. On hearing this, Bob will disconnect her service, sign the last transaction that Alice has sent, and publish it to the blockchain. Since each transaction was paying Bob a bit more and Alice a bit less, the final transaction that Bob redeems pays him in full for service that he provided and returns the rest of the money to Alice. All those transactions that Alice signed along the way won't make it to the blockchain. Bob doesn't have to sign them, they'll just be discarded. These were the three important applications of blockchain scripts. So, this was all from my side about Bitcoin scripts. Hope you all have got some idea behind Bitcoin scripts and how it works. Thank you, everyone.